Hello everyone, I'm Xiao Gang. Okay, we've actually finished covering the basic content in this chapter. Now let's talk about this extension, alright? This extension is about if there are a large number of concurrent tasks, how do we scale them? Actually, we already demonstrated this in the demo phase. Now I mainly want to emphasize a concept again. If you find this part a bit difficult to follow, that's okay. You can take a look. It's fine if you don't write it down, but you must master the previous content. So let's first review the concept we talked about earlier. First, here, obviously, we have a game thread, game thread. Then our frame rate here is 1, 2, 2, 3. Then here it's n frames. Then here it's n plus m frames, right? Then our original progress. Let's spread this out a bit. Then here is our one-step thread. These threads, they could be our runnable. They could also be from our thread pool. They could also be runnables or something. We don't care about these. Some could be from test graph. Some are defined by us. This depends on what you need. So at the very beginning, the first thing we did, the first task was in the first frame. We did A, B, C, D. After we finished this task, we went back to the first frame and then proceeded from the first frame onward. This is completely fine. Now let's erase it. So how did we do the second method? Actually, for the second method, we did it like this. Okay, we did it like this. In the first array, we defined a variable. This variable is called control flow. Then we declared it as the task named ABCD. So in the first array, we execute task A. Task A goes into the thread pool, or retrieves a thread from the thread pool. Complete tasks A through E. And we don't know exactly when it finishes. But now it has finished. It comes back to this place. Back to where we have A, B, C. So now we start executing task B, because we defined the order as A, B, C. So at this point, we start applying for constraints. It could be B1, it could be B2. I don't know exactly how many threads it needs. We only have now, actually in the previous section, we only had one thread, only the B1 case, right? Then after finishing, it comes back to do A, B, C, D. And A, B, C, D is at our bottom layer. After all of them are done, then it returns to our blueprint to interact and respond with our UI. So our entire framework is like this. If now we have a large number of cases, for example, this task A 还是否be tasks in the, or there are 10 tasks, right? So how should we design this thing? Right, if you can completely, then these 10 tasks, I need to wait until all 10 tasks are completed. Only then can I proceed. Or if just one fails, I need to cancel all 10 tasks, or cancel the other 9 tasks, something like that. But we are not considering communication between tasks. We assume these 10 tasks are all independent of each other. There should be no dependency relationships. For example, 10 download tasks, or generating 10 images, or reading 10 assets. Between them, we don't care about them. There is no communication between them. If there is communication, the situation becomes more complicated. Then here, there are 10 tasks, for example. So what should we do? Let's erase the line here first. I'll erase it first. We don't need to check this part. It's still like this here. In fact, the subsequent process is still the same. So the difference now is that this part is still B1, right? We'll just take A as an example. Then after executing A, B, C, D, then it goes back, A, B, C, D, it goes back. It goes back to the blueprint and then it just flies up, right? Then, on our end, let's assume our A here. Our A, we click here like this. This A has 10 tasks. I have 10 tasks. These 10 tasks are not related to each other. Then we take this that is all games rate. We define it as a managed task. That is, it is a managed task. It is a managed task. Of course, each task, whether managed, then this side is task. They are tasks. Then a managed task. It should have at least one task, or have multiple tasks. Then manage task. It is of course done on the main thread. Its function is to monitor whether all tasks are complete and to pass all task information to the next higher level or to external UI. etc. Manage task. Then task is for executing specific tasks. When it receives the actual task from manage task, it declares these contents. Then it declares the existing resources through itself. After finishing, it calls back to manage task. Then when manage task is destructed, it will destruct along with all tasks. Then we use smart pointers for management. Obviously, this manage task also has an ID. It has a manage task ID. Then the task also has an ID. It also has an ID. Then based on the information, we can define it more generally. But we wrote it a bit simpler here. So at this point, it also has a state. It may have an init state, a working state for success or failure. Then the task also has an init state, a working state, success or failure. So the entire framework looks like this. Then when all these tasks are completed, after they are all completed, they will carry their stats. This state, then they can return to our manage task. So it is actually at this position. At this position, we can get our 10A tasks, the result of the A tasks. Then we determine whether it is a success or failure. If they succeed, we continue to proceed. I think this result is except, for example, if 5 out of 10 succeed, I consider it a success. Then we execute task B. If fewer than 5 out of 10 succeed, I consider it a failure. Then we directly return to the UI, return to blueprint. Okay, so the framework is like this. Then we still have time. Let's take a look at this code. I can erase this part. Take a look at this code. Actually, we have already written this code before. We'll go over it again for everyone now. Obviously, here we define a struct. This struct is clearly the task struct. As for this task, it mainly has a task ID, the task status, and related information about the task. So this task is essentially about success or failure. These two are reserved segments. Then this manage task. So it is obviously, it also has this ID and then has this kind of state, except that besides success and failure, it also has a working state. This kind of state, right, this long, actually, this places on initialize or just finished initialization, has not yet entered a state. Then in this place, note that it has a tool array, and this place is a smart pointer. Then this lumber, then remember this, a task. How many subtasks does it have? For example, A1, A2. It might have 10 here. After all tasks are completed, it executes this agent. This agent is at this part of the agent. It actually returns to, look at our diagram, returns to the ABCD agent. That is, returns to our countryful agent. Actually, this part is for making some judgments. That is, which tasks we have. Has it been completed? What is the status of that task? Then this task. Actually, this place only has information. Specific task. Because it has been generalized, we can actually, in this place, write a cheap function. Write a lambda function pointer. We can say, okay, so after doing this, then in this place, within our subsystem, this part is for gammon, right? And actually there is a control flow here. This doesn't matter. Then there is a container here. This container, the GUD, is actually our managed task, and this is our ABCD. It is actually this bunch. So A is actually a key value inside it. B is also a key value inside it. So A1, A2 is actually the tailwind inside this. Yes, that's the idea. Okay, then actually we also have this kind of update here. Because we need the main thread, actually in this place we didn't use another thread to integrate all these resources. When A1 is completed, A1 actually also returns to the main thread. Then we might need to change the color. Let me see how to change a color here. Let's change the color to red. Actually, A1. This A1 returns to, for example, it returns to the second or third frame. Then it updates this manage task. Then AR might return to the fourth or fifth frame. It also updates the manage task. So this function interface, it is actually used to do this work. Right. This part is used to update the status of a specific task. Right. Okay. So we'll wrap up this lesson briefly here. Good. Then in the next few lessons, we'll do some hands-on practice. That is, if each managed task or within our counter flow, a node may need to request a large amount of resources. Then how do we implement such an interaction? The advantage of this design is because our wedge HTTP, many things are sent and received on the main thread. And callbacks are received on the main. So writing it this way is very good. This can align with the threading mechanism of UE5's underlying system. Put together. Okay, let's stop here. Thank you everyone.